Right, so here we are with CEA 2013 Physics Unit 2. First question, quite straightforward. In 60 seconds, 15 C waves pass the end of a pair. Calculate the frequency of the waves. You're advised to show clearly how you get your answer. Remember to provide the unit of your answer. Right, so I think of frequency as being waves per second. So, F can be written as what we get if we divide the total waves by the total seconds. So it's going to be 15 waves over 60 seconds, which gives us 0.25 Hertz. Nice and straightforward. Next part asks, the wavelength of the C waves is 8 meters. Calculate the speed of the waves. So this is just the wave equation in use. So V equals F lambda, 0.25 times 8, giving us 2 meters per second. In part B here we're shown this wave diagram with waves approaching a solid barrier. It says complete the diagram to show the reflections of the wave fronts at the barrier, and in your answer you should draw a dotted line with an arrow to show the direction of the reflected wave fronts and 3 reflected wave fronts. Mark on the diagram the wavelength of the incident waves. Okay. So the incident wavelength is this gap here. So our direction, we came in here along the diagonals, so we're going to leave along the diagonals. And I don't have a straight line pen tool here, so I'm going to just do my best, come along the diagonals. Obviously you would use a ruler. So we're going to come along that way and we're going to show the direction. Reflected wave fronts are going to be again along diagonals because these are going to be reflected. We've got a 45-degree angle of incidence, we've got a 45-degree angle of reflection, which means our wave fronts are going to reflect along this direction. And you can see we come 1.5 diagonals out from the direction shown, so we're going to have to do that here also. So I'm going to come out from here 1.5 diagonals, which is really like that, and 1.5 diagonals here, and 1.5 diagonals here. Right, so what about this other question? In what way do all the frequency, in what way, if at all, do the frequency, wavelength and speed of the water waves change when they are reflected? Indicate your answer by placing a tick in the appropriate boxes. Okay, so what we need to remember is that frequency across a boundary is constant. Waves arriving at the boundary equal waves leaving the boundary, so the frequency is not changed by any of the properties that we come across. Both incident and reflected waves are in the same medium, so their speed will be the same. And both incident and reflective waves, since frequency and speed are the same, will have the same wavelength. So the answer here is going to be unchanged, unchanged, unchanged. This is not what happens for refraction, but in this case we're dealing with reflection. Both waves are travelling in the same medium, and so everything stays the same. Frequency, speed and wavelength all stay the same. during reflection here. Okay, if it was refraction, then there would be a speed change and there would be a wavelength change. Frequency never changes, as I said, but we're not dealing with refraction, so there's no speed change and there's no wavelength change. Part C. To study the reflection of sound from a solid object, the apparatus below was used. So we've got an electronic timer, we've got something to send out a pulse and receive that pulse back, and the emitter and receiver here is a set distance d from the reflecting object. It says a pulse of sound was emitted by device at A, and the time taken for the sound pulse to travel to the object and back. So they're emboldening this phrase. So it's all the way there and back is the time. Round trip time was measured. This was repeated for different distances d, and the results of the investigation are shown in the table below. So they show you the table and they ask you to complete the table. So you're getting 1 mark for recognizing that these time to travel a distance d are going to be half of all of these times. So basically you have to half all of these numbers and fill them in down here. It says using the equation below and data from the table, calculate the speed of sound. So we're told that 1 millisecond is equivalent to 0.001 of a second. And so we take some data from the table. Probably the biggest numbers would be the best. So if we take that distance of 1 meter and the time to travel, that is 3 milliseconds. Speed is distance over time. 1 meter divided by 0.003 of a second, giving us 333 meters per second. Now we're asked to plot the values from the graph, and in particular we're being asked to plot the distance d versus the time to travel a distance d. So it's the third column that we calculated that we're being asked to plot. So the first point is at 0.6, which is here, and 0.2, which is here. So we're looking at the intersection there. And so we need to plot that and the other points present there. So you end up with something like this. And a best fit line, something like that. Now we're asked to determine something from the graph. It says the sound emitter was placed at a distance from the object that gave a round trip time of 3 milliseconds. Using the graph, determine the distance d. So a round trip time of 3 milliseconds is going to correspond to 1.5 milliseconds on our graph. So we need to have a look at the graph and put those values on. So we zip a line up at 1.5 milliseconds and take that across to the other axis, and we find that's coming in there at about 0.5 of a meter. So we just transfer that down. And that's it. Diagram in question 2 shows a ray of light incident on a glass block. Some of the light is reflected at the top surface and some of the light passes through the glass and is reflected at the opposite side, which has a mirrored surface. So it says complete the path of the ray through the glass block and back out into the air towards the person viewing it, as shown in the diagram. So this light is entering glass, so it's going to bend towards the normal here, which means it will come down like this. remember, light entering glass slows down and bends towards the normal. It's then going to be reflected, so you've got reflection going on here, and then it's going to leave the glass and bend away from the normal. So bending towards the normal on the way in, so you imagine this is original direction, it's going to come down a bit from there, be reflected here, and then bend away from the normal on its way out. And actually, because of the arrangement here, the angle coming back up is going to be the angle that it went down at. So this is going to end up going parallel to the original ray, but I don't think you're expected to know that. Okay, so this ray comes in like that, turns, heads to the mirror, it's reflected according to the laws of reflection here, and then it bends away from the normal on its way out. Part 2 asks us to state the two conditions required for a ray of light to undergo total internal reflection as it moves from one substance to another. Now we need to remember what goes on in total internal reflection. If you imagine this is the glass and outside here is the air. Light has to be trying to leave a dense medium and enter a less dense medium. So that's one thing that has to be true. Secondly, you remember that as the light goes out, it's refracted. As you go up to steeper angles, it's refracted more. As you go to the critical angle, it's refracted along the edge like that. Anything beyond the critical angle gets totally reflected. So you've got two things. The light has to be trying to leave from air, or from glass to air, and it has to be at an angle of incidence with the surface that's greater than the critical angle. Those are your two facts. Right, part 3. David was investigating how a ray of light passed through a semicircular glass block. He drew diagram 1 below, however he made a number of mistakes. Using diagram 2, draw the correct paths of the two rays that he drew wrongly. First thing you should do is get a normal onto this diagram so that you can think about what is happening. Now this ray was travelling in that direction. When it leaves the glass, it's going to speed up, and that will result in it bending away from the normal. Okay, he has it bending towards the normal. The original direction was like this. He's got it bending closer to the normal, but it's going to speed up and bend away from the normal. So it's important that that fact is included here. So we're going to get a bend that's down slightly from its original direction of this way. Okay. We're also going to have to deal with the reflected ray. Now the reflected ray here is not coming back with an angle of reflection equal to the angle of incidence. That's what's wrong in the second case. So we need to draw a more realistic angle that's equal to what happened on this side, this angle here. We need a similar behavior on that side. So we want one that looks like it's reflecting at the same angle as the angle of incidence. Okay, so bending away from the normal because it's speeding up, and an angle of reflection equal to the angle of incidence. Part 4. The red reflectors found on cars and bicycles use total internal reflection to allow road users to see the back of another vehicle. The diagram below shows part of such a reflector, and on the diagram complete the path taken by the ray of light shown. So this is a 90-degree reflecting prism. The light's going to come in. It's got an angle of incidence of 45 degrees here, so it's going to come off at 45 degrees. That will result in it going straight down. Then it's going to hit here at 45 degrees and come back at 45 degrees. So we've got in, straight down, and out again. So it's a reflecting prism, and because of the angle that it's sitting at, we're going to get that path. Just simple reflection at two surfaces. Part B here, we're going to have to draw a ray diagram for this object using the rules of drawing ray diagrams. But first off, we're told that the lens has a focal length of 3 centimeters, and this thing is shown full scale. So the principal focus has to be marked on here, and that will be 3 centimeters out. So here we go, 1, 2. So the principal focus is going to be here. It also says then, draw 2 rays on the diagram to help you find the position of the image. Label the top of the image with the letter I. So there are basically 2 rules for lenses. Any ray going through the optical centre will pass on undeviated, like that. And any ray that's running parallel to the axis will turn and go through F on the other side. So we're going to come up to here and then turn and go through F. So a ray through the optical centre that passes straight on, and a ray here that turns and goes through F. Now this is quite difficult on the iPad because Explain Everything has no straight line tool, so you'll have to bear with me with this. So this second ray has to turn now and go down through the focal point, and we end up with this. So by dotting these rays backward along their paths, we find a point where, if you're looking in from here, these 2 rays appear to come from some common point back here, and so that's where your image is going to be. So we add in our image and label it as we were required to do. We were also asked to put arrows on to show the direction of light travel in both of these cases. It's worth noting that this is very hard to do on the iPad, when I did this on paper I found the image to be here, but just for realism I've put the image where the iPad rays show it to be. But obviously if you're able to be more accurate on the actual page, then you should get the image where it belongs. So then, is this image real or virtual? Explain your answer. Okay, so let's have a look at this. So these rays are never going to meet. These are never going to meet again. They will not form an image on a screen. They only appear to meet from an observer looking in here, sees them as coming from a common point back here. So this is definitely a virtual image, and the reason it's a virtual image is because the rays don't actually meet. It's marked with the letter E, the approximate position you should place your eye in order to view the image. Okay, so you should be putting your eye roughly here and looking in. And that's it. Okay, now this question starts with a lot of waffle about this particular experiment. The important thing is that the nature of this experiment isn't just as important as the numbers coming from it, because most of the questions are about the table of results. So we had here the idea of looking at the image distance and object distance for a particular object that you're showing out on a screen. It says to investigate the properties of the image formed by converging lens, Mary set up the apparatus shown below. She placed an object at various distances from the lens. The object is a wire mesh illuminated by a lamp. So it's basically a grid of wires which you can then tell when it's in focus. For each distance, she then moved the screen until a sharp image of the object was seen on the screen. Mary measured the height of the object, and then she measured the height of the image obtained at various positions. She calculated the magnification of the image using the formula magnification equals height of image over height of object. And the table below shows her results. So you've got this table of object distances and image distances, and then the corresponding value of magnification, which she found by measuring the heights of the object and image. The first question asks you, by examining Mary's measurements, deduce another method for calculating the magnification produced by the lens. So you can see these numbers here. When we had 25 and 100, the magnification turned out to be 4. When we had 30 and 60, the magnification turned out to be 2. When we had 35 and 46.7, the magnification was 1.3. When we had 40 and 40, the magnification was 1. And we had 45 and 36, the magnification was 0.8. So clearly, image distance over object distance is also giving you these magnification numbers. And so that's what you're meant to say, that the magnification is going to be the image distance divided by the object distance. So we get magnification equal to image distance over object distance, and then you're asked to provide some calculations to show that it was true. So you just put a couple of calculations in that show that it is coming out to be the correct value. It says then below, what happens to the size of the image when the object is placed further than 40 centimeters from the lens? So you can see in the table, if you're looking at it, that 40 centimeters is where we got a magnification of 1. And for an object placed further than that, then the object distance is greater than 40, and it goes to 0.8 then, which means the magnification is getting less than 1, which means the object is being made smaller, or the image is being made smaller than the object. And so the image will be smaller than the object at that point. Question 3. Zoe was given a sealed box containing a component that conducts electricity. The two terminals attached to the box allowed her to connect it to a circuit. To find out what the component was, she decided to investigate how the current passing through the component depended on the voltage across it. Complete a circuit diagram below by inserting a switch, an ammeter, a voltmeter, and a variable resistor that would allow Zoe to obtain a series of values for the voltage and the current. So we're going to put a switch here, here. We're going to put our variable resistor here. We're going to put an ammeter here because ammeters have to be in series so that they can measure the current of something in the loop. Remember, in a series loop, current is the same everywhere. So an ammeter must be in series with whatever you're trying to find the current in. Where does the voltmeter go, you ask? Well, voltmeters have to go in parallel with the voltage that they're trying to measure because voltages across things in parallel are the same. So we end up with a circuit like this. So they show you this graph and then they ask you some questions about it. So using the graph, calculate the resistance of the component when the voltage across it is 5 volts. So we're going to have to go here to 5 volts, go up to the graph and go across to the value corresponding to that. So at 5 volts, we have this value which is 1 square above 0.6 of an amp. So if this is 0.6 and this is 0.7, then each one of these squares is 0.2. So this is 0.62 of an amp. So R equals V over I. That's just Ohm's law. 5 over 0.62. That comes out to be 8.06. I'm just writing it down as 8.1 ohms. And we don't need to write ohms because the unit is given. Now, is the current proportional to the voltage? Explain your answer. Well, the current is not proportional to the voltage. There are two conditions for proportionality. One, that the line goes through 0, 0. And two, that it's straight. Both of those things have to be true for the two quantities to be proportional. So we need a straight line that also goes through 0, 0. But we don't have that. So the answer is no, and the reason it's not a straight line through the origin. So the answer is no, and proportionality would require it to be a straight line through the origin, which it isn't. Does the resistance of the component remain constant as the voltage and current are changed? Explain your answer. Well, resistance is V over I, and this ratio of V over I would be the 1 over the gradient of this. So in order for that to be constant, the gradient here would need to be constant, and it isn't. So again, that would also require a straight line. So that's a no, because we don't have a constant gradient. Another way to say it is that if V over I is not a constant, then R is not a constant. And we're asked then, what type of component is this? So we need to look at the way this graph moves. Proportionality would be a straight line like this. It's bending this way. What's happening here is that to get this amount of current required 2 volts. So to get 0.3 there required 2 volts. To get 0.6 required more than 4 volts. To get 0.8 required nearly 8 volts. So 2, 4, 6 if it was proportional. It's getting harder to get the extra bits of current. So the resistance of this is increasing. Now the graph we learned for that, where resistance is increasing as you put current through it, is for the filament bulb. I would always tell people that, they may plot this the other way around, but what happens in this graph is that it always bends away from the current axis. So when you're looking at a filament bulb graph, it'll be bending away from the current axis. So it's a filament bulb. Okay, calculate the total resistance of the circuit in the diagram. Now it's important to note that this can be thought of as something here in series with something here. So a resistance here in series with that. So our first task is to look at these two and do a parallel calculation to figure out what the resistance of this combination is. Then we put it in series with the other one. Now the series part's easy because when resistors are in series, we will just add the answer here to this 3 ohms. So this is the tricky part, finding this first. So the first thing I would do is redraw the circuit as a parallel resistance, which we call RP for parallel, in series with the 3 ohms. So we're going to have to do a calculation for that 8 and that 6 to get an RP value. So when we have 2 resistances in parallel, then 1 over RP equals 1 over R1 plus 1 over R2, where R1 and R2 are the 2 resistors we're talking about. So R1 was 8 ohms and R2 was 6 ohms. So we'll need to take a common denominator here. And if the common denominator is 24, then an 8th written as 24ths is going to be 3 of them, and a 6th written as 24ths is going to be 4 of them. So that's 7 24ths. Now this is where a lot of people slip up, because that is an answer for 1 over RP. RP will be this upside down. So RP is 24 over 7, which works out at 3.43 ohms. Our total, the series part, will be RP plus the 3 ohms, because when you add resistors in series, you just add them together. Combining them in series, we simply add them. And that gives us 6.43 ohms. And again, the unit is already given. Okay, so we've got a circuit bit like this. We're asked to calculate the current flowing in the 3 ohm resistor. So if you look at the original diagram, the 3 ohm resistor is in the main branch of the circuit. The parallel section doesn't really matter. If we can find this total current here, we will be finding the current in the 3 ohm resistor. So we have a total resistance of 6.43. We've got a total voltage of 12 volts. That means that I total is just going to be V over R total. And that's going to be 12 over 6.43. And so we get 1.87 for that. And that's going to also be the current in the 3 ohm resistor. Part C. Jack rubs a plastic comb on his jacket sleeve and it gains a negative electrical charge. He then uses the comb to pick up small pieces of paper as shown in the photograph. Explain in detail how the comb acquires negative charge and how it is able to pick up small pieces of paper. Remember, the pieces of paper are not electrically charged. So there's some important information here. It's a plastic comb rubbed on a jacket sleeve, and importantly, we get a negative charge. So we know that the plastic comb ends up negative. He then uses the comb to pick up small pieces of paper. So how do we get the comb charged? Well, there are 2 objects. There's the jacket sleeve and there's the comb. We have to explain that electrons, which are negative particles, transfer from the sleeve to the comb. That's how it gains a negative charge. Electrons is a term you should know. Okay, you should be naming the moving charged particle that happens to be the moving thing in electrostatics problems. So we have electrons transferring from the jacket sleeve to the comb, and that gives the comb a negative charge. How can it then pick up the paper? So what happens is the comb has too many negatives, and when you bring it near the paper, it repels electrons in the paper away from it. What happens then is that the attraction to the remaining positive charge on the nearer side causes the attraction to dominate, and so the paper, even though it's neutral, because its charges redistribute, it jumps over onto the comb. So you need to explain, firstly, that the electrons are going from the sleeve to the comb. Secondly, it repels away electrons in the neutral bits of paper, and the attraction to the remaining positive charges dominate because they're closer, and so it can attract and pick up the paper. So here we have a little induction question. With a magnet being moved in, we've got a galvanometer here to register the direction of the current, and we've got a south pole being brought in here. Now it says, describe carefully what is observed when the magnet is slowly moved into the coil from the right, held there stationary for a few seconds before being removed quickly. So we've got slowly in, quickly out, and stationary in the middle. Coils like this only react to changes in the magnetism, so you're only going to see something on the meter while the magnet is in motion. And since the motion is causing it, faster motion creates faster motion here quickly on the way out creates more electricity from the system than slow moving magnets would. Okay, so we want to say that there's a deflection on the meter when we bring the magnet in. So as the magnet moves in, there's this deflection on the meter. What happens then is that when it's stationary, the meter quickly goes back to 0 and stays there. And then when we quickly remove the magnet, we get a deflection in the opposite direction to the way it went the first time, and it's a stronger deflection. So say we got this the first time, we get a much stronger pointer pointing much further over on the way out, because we put it in slowly. That creates a small amount of electricity. Pulling it out quickly produces a larger amount in the opposite direction. So small value on the way in, still in the middle at 0 when the magnet isn't moving, and then a strong opposite value on the way out. Part B. A transformer has two coils, one of 100 turns and the other of 400 turns. The transformer is required to change the input voltage from 6 volts to 24 volts. And then you're asked to label the correct numbers of turns at each side and which one has which voltage. Okay, now the important thing to remember with transformers is that the voltage always follows. It's higher where the higher number of turns are. Okay, so if you're asked to identify something like this, the high voltage will be at the side with the high number of turns. So 100 turns is the smaller number and 6 volts is the smaller number, so they will be on the same side, the 100 and the 6, and the 400 and the 24 will be on the other side. Now I'm just going to assume that this side here is the primary and this side here is the secondary, but it'll not matter as long as you have them on the correct side. So we've got 100 turns on the low voltage side, 400 turns on the high voltage side, 6 volts going in, 24 volts coming out, and that's it. So we're then asked to complete this table, identifying the type of voltage, alternating or direct, and tick the box. Now if you remember the last problem where we were producing electricity by induction, the system only reacts to changing magnetism, and the transformer is no different. It's only when there's a changing voltage going in that you get changing magnetism. And so we can only feed AC to a transformer. It will not pass DC because DC will produce steady magnetism and the output coils will only react to changing magnetism. So we'll send AC into it and we'll get an AC voltage coming out of it. Power stations in Northern Ireland generate electricity at a voltage of 25 kilovolts. That is then stepped up to 115 kilovolts before it is connected to the overhead transmission lines. Explain fully why this is done. Okay, so this is to do with efficiency. When we transfer power from one place to another, we're transferring voltage and current. So as long as the product of voltage and current gives us the amount of power that we were asking for at the other end, we don't really care about how it is transferred. What we choose to do is transfer it with a very high voltage, and that allows us to transmit with a much lower current. So if we use a very high voltage, we can send it with a lower current. Why would you want to do that? Well, the transmission lines between the pylons are going to be where you can lose some energy, because the current will turn into wasted heat energy, okay? Because the power wasted there is going to be I squared times the resistance of those cables, and that can be very wasteful. So what we choose to do is use a high voltage. That allows us to use a very low current and reduces this wasted energy. So by using a high voltage and a low current, we can produce transfer of electricity from one place to another much more efficiently and with much less energy wasted as heat. Part C. Fleming's left-hand rule is illustrated in the diagram below. So you've got here a left hand with the thumb pointing up, the pointing finger pointing straight ahead, and the second finger pointing straight out from those two. Label each arrow with the quantity it represents. Okay, so your pointing finger is always magnetic field. Okay, Your second finger is always the current. And the thumb is often referred to as the thrust or push or force. Okay. There's a video elsewhere on my channel on the left-hand rule. You might want to take a look at that. Diagram below shows a wire carrying a current. The wire is placed between the poles of a magnet. In what direction does the wire experience a force due to the current? Okay, so my awful drawing of a left hand in the correct position here hopefully is showing us what we need to know. The field is going straight across like that, so we've got our field finger pointing straight across. Remember, field flows from north to south, so it is going across that way. Current is going this way, and so we've got our current finger pointing the correct way. When we've got our current finger and our magnetic field finger pointing the correct way for our left hand, we find that our thumb is then pointing up at that point, which means the force on this wire will be an upward force. Part 2 says describe how that would change if the current used was alternating. Now, that's not going to change the field direction. That's going to continue to be across there. But if the current went from going this way to going that way, that would involve your hand having to reverse with your second current finger pointing the other way, and that would push your thumb down. If you kept having to flip your hand from current going this way to current going that way, you would have to rotate your hand through 180 degrees to get your finger pointing down this way, and that would also rotate your thumb through 180 degrees, and your thumb would be pointing down. So the current reversing would cause the force to reverse, and so you would get up down pushes as a result of that. Okay, so we would get up and down. Basically, it would produce a vertical vibration. Okay, so the force would then alternate between up and down. Part D. To investigate the strength of the magnetic field produced by the current in a coil, Gail set up the apparatus shown below. Gail closes the switch. What should she now do to change the current in the coil? Okay, so obviously you've got this variable resistor here, and it can alter the current. So changing the current in the coil can be done by adjusting the slider on the variable resistor. On the diagram in the boxes provided, mark the polarity of the magnetic field produced when a current flows in the coil. So we have to identify these poles. So first we have to identify the direction of current flowing. So as you can see, we've got a positive terminal here, which means the current is coming up when the switch is closed this way, so it's going across that way in all of these coils, and then it comes back this way. So that's all you're doing at that point. You now need to look at this section with the magnet and try and imagine you're looking through it. Okay, so if we look through from the bottom end, these wires are coming over the top. So if we look down from this end, the current is coming over the top towards the right, and underside it's going to the left. Now, to identify the poles, you just take the letters belonging to them and add arrows to them. If you can see anti-clockwise current flow, then you're looking at the North Pole. If you can see clockwise current flow like this one, you're looking at the South Pole. Now clearly from this end, if we were to look up from this end, look up through here, we would see clockwise electricity flowing, and that means this end is the south. Okay, and this must be the north. The iron core is replaced by a wooden rod. What effect does this have on the strength of the magnetic field? Okay, remember what happens is that the iron will become a magnet itself, and lots of the little magnetic domains within the iron will all line up and enhance each other, and so that normally produces a much stronger field than the coil on its own. The wood has no such properties, so it cannot enhance the field due to the coil. The field due to the coil is usually relatively weak. It's the iron that enhances it significantly. So it says, what effect does this have on the strength? And the idea here is that the strength would be greatly reduced. Okay, question 5 of the space questions. What are the two main elements or main constituents of stars? And hopefully you know that that is hydrogen and helium. That's just a learning off thing. The process responsible for the energy in stars is nuclear fusion. Stars continue to produce energy for a very long time. What two forces are in balance to maintain their stability? And remember, that's a fight between the gravity crushing it in and the radiation pressure forcing it back out again. Describe and explain briefly the nebular model for the formation of the solar system. In your answer, you should give one piece of evidence that supports the model. So we have a giant cloud of gas and dust that is then contracted in, forced inward by gravity. That causes temperatures to rise. When it gets hot enough, we get some nuclear fusion at the center, and that will produce a new star, which in our case is the Sun. The heat at the center forces gas elements further out, and that's why we get gas giants further out with rocky material closer in. And so we would expect the solar system to have dense planets close in and gas planets further out, and that's what we find. So we've got a set of planets in the same orbital plane, so they're all orbiting on the same flat disk, and then we have also the second idea that we get rocky dense materials close in and gas material further out. Part C then, read the paragraph below. With a traditional optical telescope, the space between the stars and the galaxies is completely dark. A radio telescope detects radio waves coming from space. A very sensitive radio telescope can detect a faint signal coming from all directions that is not associated with any star, galaxy, or other object. What is the name given to the faint signal referred to in the passage above? And hopefully you've learned that that is the cosmic microwave background radiation. Cosmic microwave background radiation. And again, hopefully you've learned off that that is the afterglow of the Big Bang. So when there's a Big Bang, any explosion, there's a rise in temperature and then that fades. We expect that the temperature of the universe has gone down to this value where the radiation coming off will be in the microwave radiation region. So it's the afterglow of the original Big Bang. Part D, 1. Galaxies are moving apart. What observation provides information for this conclusion? Okay, this is because their light is shifted to the red end of the spectrum. And that means they're moving away from us. So we're shown this graph, and it says each dot on the graph below represents a galaxy. The distance d from our galaxy, the Milky Way, to each galaxy is plotted on the x-axis, and the velocity v with which the galaxy is moving away is plotted on the y-axis. Okay, so this is Hubble's graph relating the speed at which galaxies are moving and comparing it with how far away those galaxies are. And you can see that there's a correlation between them. The distance and the velocity are related, and that makes sense if the close galaxies came from a certain place and the further away galaxies came from the same place. The high speed ones would take longer to reach, or would take the same amount of time to reach a greater distance, and the very high speed ones would take the same amount of time to reach an even greater distance. So that's why we're getting this proportionality. Describe what this graph tells us about the motion of the galaxies. Okay, so the further out a galaxy is, the faster it is moving away. Okay, the distance to galaxies is measured in light years. The relationship between the velocity v and the distance d is known as Hubble's law and is written in the form that v equals h times d. The velocity v is measured in kilometers per second and the distance is measured in millions of light years. H is a constant known as Hubble's constant, and its value is 25 kilometers per second per million light years. The Hercules galaxy is 670 million light years away from the Milky Way. Calculate the velocity at which this galaxy is moving. Okay, so it's 25 kilometers per second per million light years. So we've got 670 million light years. And there's 25 kilometers per second for each one of those million light years. So V equals HD, Hubble constant times how many million light years it is, gives us 16750 kilometers per second. The final fate of the universe is not really known. The graph below shows two possible fates of the universe, the big freeze and the big crunch. On the graph, label which curve corresponds to each of these possible fates. Okay, so crunch is when it expands out, just like when you throw a stone up, and comes back down and crunches to a tiny size again. Freeze is where you throw a stone up so far that it just keeps on going. And the universe just gradually gets cooler. So this is the crunch, and this is the freeze. Okay, so you're expected then to explain the big freeze and the big crunch in terms of what they mean for the fate of the universe. And the idea of the freeze is that the universe will just keep on expanding and gradually cool, which is why they call it the big freeze. And then the big crunch is where gravity is strong enough to bring the universe to a halt and send it gradually falling back on itself. As I said before, the idea that if you throw a stone up, it goes a certain distance and then gravity brings it back. But if you throw a stone up hard enough, it does escape from the Earth. So we may find a universe where that happens, where the stuff is flying apart fast enough that gravity will never slow it down and turn it back. But we may find that the crunch happens and that gravity does turn it back, and so the universe will come back to a tiny point again, like it was in the original Big Bang, crunch back on itself. Question 6 starts off with just some basic bookwork about the various layers coming out from the center of the Earth. And it asks us to fill in a table. So we're asked about layer A here and whether it's a solid or a liquid. Well, hopefully you'll realize that layer A there is the crust, the upper part, the total upper part of the Earth's matter is the crust, and it's definitely a solid. We've also got a space to fill in for B, and hopefully you'll remember that that is the mantle. And it is in different states depending on where you are in the mantle. So you get away with solid stroke liquid, or a bit of both for that. And then we're asked about layer D, which is right at the center. So that's our inner core. And it is a solid. And composition, well, same as the outer core, nickel and iron. So now we're shown this map, and we're told that the dots show the location of earthquakes and volcanoes, and you can see that they come in little lines in various positions. And so we're asked, what does this suggest about this upper topmost layer of the Earth? And so this is the idea that it's in sections called plates. So how does the structure of the Earth, suggested by diagram B, explain things like earthquakes? Well, the idea is that these plates are in motion, and it's when they're bumping against each other and shuddering past each other that we get earthquakes. So you can see there's 3 marks for this. So if I put my finger on the iPad case and put a sideways force on it, you'll probably hear through the microphone that every now and then my finger slips and shudders across the case. And that's what's happening with the plates. They stay in contact with each other and then shudder, and that shuddering movement as they slip past each other is what's causing the earthquake. So I've just said that the plates are moving very slowly, and every now and then their edges slip and shudder past, with one going down, one going up, like that. And the shudder is an earthquake. How are volcanoes explained by the structure of the Earth? Now, unfortunately, your specification is very vague on volcanoes and earthquakes. It just says that you're supposed to understand how they're formed. It doesn't explain the specifics of what you're meant to be told. The mark scheme, unfortunately, for this paper just talks about friction, and that's creating heat and that's melting rock and making magma, but to be honest, it's not really friction. Volcanoes are mostly formed at converging or diverging plate zones. So in converging you get subduction, and in subduction you've got one plate subducting under the other, and what happens is that the rock is melted here, and there's organic material also being brought down here and melted, and that produces tremendous amounts of gas. And so between the melted rock, the magma that's forming, and the pressure of the gas, that material is forced up, and that's what gives you the earthquake. Now, they're also formed at places where 2 plates are drifting apart, and so new material is coming up and forming new, it's often under the ocean that happens, and there's new ocean floor formed when that happens, but I would imagine that just explaining the subduction system here would have been enough, that you've got one plate going under the other, that material is then being melted, and that's producing magma, which is then forced up to an eruption. Unfortunately, as I say, the mark scheme's very vague and just talks about friction making heat, which will melt some rock and make magma. But I would explain it in these terms if I was talking to my class. Okay, so diagram 1 shows how the continents might have looked many millions of years ago. Diagram 2 shows how they look today. So you can see from the title here, this is a picture of what was referred to as Pangaea, where the continents were all those years ago. And it says, describe the process which brought about this change. And so we explain that the continents that we have are on top of the plates that are moving, and over millions of years the plates have moved to new locations, and that is why we have the same continents in different positions now. Okay, so the continents are actually on the plates are moving, and over millions of years they have then moved to new locations. And that, as they say, is that. Thanks for watching. And of course, good luck with your exams.